exactly is a solenoid? A solenoid can either be a wire wrapped into a coil, which is just called a solenoid, or a cylinder, which is referred to as a continuous solenoid. Our design calls for a finite solenoid, which is to say, a finite length of wire wrapped into a coil. Because our solenoid is finite, the position of the ball bearing has an effect on the force due to the magnetic field. As the B field, or magnetic field, is weaker towards the ends, this difference is negligible at this level. The magnetic field can be produced by a wire by sending a current through it. Therefore, when the wire is coiled, or in other words, a solenoid, the magnetic field in the center of the coil is amplified by each loop. As the wire coils, the magnetic field, which is always perpendicular to the wire, bends as well, and through this, the magnetic fields build on one another, creating an even stronger field. Solenoids are fairly limited in their practical applications, which consist primarily of electromagnets used to charge objects by induction, launch metallic objects and objects with a Coulomb charge, and move mechanical parts such as cymbal locks and aerospace release mechanisms. Electromagnets work due to the magnetic field pushing all of the electrons to one side of a metal object. When another object is placed near the negative end of the electromagnet, the electrons in the object are repelled. Therefore, if a wire or some other grounding device is in contact with the object, the electrons will be pushed into it, and when the ground is removed...
So now we get to the boring part, the math. We start with summing our forces for our coil gun. Using Newton's second law, we see that the net force equals mass times acceleration. Well, the force is acting on this, gravity and a B field. So now we move on. Our force of B field minus the force of weight of our ball bearing equals the mass of the ball bearing times its acceleration. We found that our ball bearing is only about 6 grams. Convert that into kilograms, and voila, our force of weight is done. The B field is a little bit more tricky. We know that the force of our B field is equal to the strength of our B field, B, times the current through the wire, I, times the length of our wire, L. F equals BIL. Next, we need to calculate the strength of our B field. Our equation sheet tells us that the B field strength is equal to the number of coils, N, times mu naught, which is a constant, times the current through the wire, divided by the quantity 2 pi times our radius. Now, the pipe that our coil is going to be wrapped around is about 1/2 inch in diameter, so the radius is about only 1/4 inch. Convert that into meters, and then the only thing we're missing is the current. Ohm's law tells us that current is equal to the voltage divided by the resistance. Assuming that we have a full charge on our capacitors, and they're all hooked up in parallel, we know that our voltage total is equal to 1,320 volts. Assuming we have a full charge on all of our capacitors and they're hooked up in parallel, we know that our voltage total is equal to 1,320 volts. Because we know that we have no resistors in our circuit at all, at least none on the firing end. The only thing we need to worry about is internal resistance. Now, the equation for our internal resistance of our wire is equal to rho times the length of our wire divided by the cross-sectional area of our wire. Square the radius of our wire, multiply by pi, and we have our area. Multiply all the numbers together, we have our resistance. So now we have our resistance. Here's our voltage, 1320 volts. Divide that by divide the 1320 volts divided by our resistance, and we get our current to be pretty darn high. For those who care, it is not the voltage that kills you, it's the current. It takes a total of 10 milliamps to kill you. So as you can tell, this is incredibly dangerous stuff. Now with our current calculator, we can calculate the strength of our B field. We get take mu naught times our number of coils times our current divided by 2 pi r, and we get the strength of our B field. Multiply this number by all of our current and the length of our wire, and we get our force at the B field. Subtract this from the weight of our ball, divide the mass of our ball bearing, and we get a really high acceleration. Well, this is all great and all, but if you saw our shot, why does it only fly about like 5 feet in the air before coming back down? We figure that when we turn on our circuit, the electricity travels at the speed of light through our wire. So if we take the length of our wire, divide it by the speed of light, we get our time to be 5 times 10 to the negative 8 seconds. This is extremely fast. Take this number, takes our time, times our acceleration, and we get our final velocity. this thing is a deadly projectile.
Here's a simple circuit diagram of our coil gun. We start with a AA battery, which has a voltage of 1.5 volts. The current then goes through 4 capacitors of varying capacitance, but with equal voltage, 330 volts. Once the capacitors reach a full charge, which we determine to be when the humming stops, we flip the switch. The current, now increased by the increased voltage, then flows through the metal switch and then through the solenoid, where a magnetic field is produced, projecting our metal bearing.